Hi everyone, Queeveen here from the comfort of my kitchen. In today's video, we are going to very quickly, this will be a bit of a rapid fire video compared to my other videos at least. We're going to quickly take a look at some of the misconceptions that people may or may not have about space. The first off is the color of the sun. And in general, people draw the sun as yellow. The actual color of the sun doesn't really matter too much. We don't normally get to see the sun without all of this oxygen and nitrogen in the way. And the light of the sun gets broken up, scattered or refracted by the atmosphere. The exact physics behind why the sky is blue and why the sky looks the way it does is a little complicated. But suffice it to say that what we're seeing is the sun distorted by our atmosphere. Never look directly at the sun. But the sun does seem to have a yellowish tint to it, while the sky appears more blue. In reality, the sun is pretty close to white, kind of a whitishy green, white, blue, whitey green kind of color. We call the sun a yellow dwarf mostly because it's small, and it is cooler than a lot of other stars. White dwarfs are hot, and blue stars, giant white stars, those are quite hot. The sun is kind of a middling star. It's not crazy hot, but it's also not as cool as a red or orange star. Stars can get a lot hotter than our sun. But our sun is not a burning ball of gas, nor are any of the other stars. So the sun and all stars go through a process of nuclear fusion, where light elements, light atoms, are fused together into heavier forms. Atoms crash into each other, pick up little bits of other atoms, and eventually end up being bigger and heavier. Atoms are composed, or atomic nuclei are composed of protons and neutrons. We don't really have to worry about the electrons, because plasma is a soup of protons and neutrons, atomic nuclei, surrounded by electrons that are usually free from the atomic nuclei that they would be attached to in cooler substances. This is a general trend when it comes to the phases of matter. If you're looking at a solid, then all of the electrons and the atomic nuclei, they're all bonded very, very close together, very often in solids of various types. The individual atoms are locked together either through ionic forces or through some other means. Then when you start heating things up, you get liquid, where the molecules are still bound loosely together, but they can flow around each other. And then you get up to a gas, where either the molecules or the individual atoms, they're floating around without really any bond to their neighbors, but their electrons are still bonded to them. When you get up to the state of plasma, then you get electrons flowing around a little bit more freely. And the atomic nuclei then, made of their protons and neutrons, they crash in together, extra protons get added, extra neutrons get added, some of them fly away into space, and energy is created. And that's how the sun generates heat. It isn't burning only because burning means oxidation. And if we were to broaden the category of burning, when people say nuclear fire, sometimes it's a normal fire started by a nuclear explosion, sometimes it's the actual nuclear activity, which is normally fission in the nuclear stuff that we see down here on Earth. But really saying that the sun isn't burning, the sun isn't burning if by burning you only mean fire. For example, if I spill acid on my hand, it's going to burn. It will feel like it's burning, even though what's going on isn't necessarily fire. It isn't necessarily the same oxidation reaction we get when things burn. People still call it burning. The sun isn't a burning ball of gas, it's a burning ball of plasma. And by burning, I really mean nuclear fusion, but we don't need to get bogged down in those kinds of details. The sun's really, really hot, and that is the important thing. And it's hot out there in space without any gas around it. Most of the things near the sun are plasma. If we move on towards nighttime a little bit, we can see our dark sky here, and a lot of people do assume, this is a misconception that I believe, that the stars are dead, that the stars are burned out, that the stars are so far away that their lives have ended. And that may be true for some stars. But if we take a look at Vega here, Vega is, if I can find out how far away from us Vega is, 25-ish light years. That star is not after dying 25 years ago. That star hasn't died within the past 25 years. If it did, if that star died within the past 25 years, its light would still be reaching us. Absolutely. We wouldn't know until the 25 years had elapsed. But by looking at stars like Vega, like other stars, we can get a pretty good idea of their age and how long they're going to last. The shortest lived stars still last millions of years, And the furthest away stars that we really see in our sky are only thousands of light years away from us. For the vast majority of more distant stars, where we are actually seeing them after they've blown up, well, you need a telescope for them. They're way, way more distant. For some stars, it gets a little bit more. There's a little bit more of a chance. So Betelgeuse should just be coming up in the morning. That's Aldebaran. We'll move forward just a few days to get Betelgeuse into the sky. There we go. There's Betelgeuse in Orion. And this is an old star. Betelgeuse is a big red giant. It is swelling up, it's getting old, and it is about 500 light years, give or take 50 odd light years away from us. Betelgeuse may have blown up within the past 500 years and we don't know about it yet. That is one of the few stars that we could be looking at the light of a star that's already blown up. It's not very likely for most of the other stars that we see in the sky. Pollux is a short-lived star. I believe Pollux is one of the bluer stars. BV, no, that's not too blue. If we take Castor there. So these stars, they are hundreds of light years away from us. Well, Castor is only 50. This one's only a few hundred. Or no, only 33. Yeah. Within the past couple of decades, those stars absolutely haven't exploded. They just look too young. And we can see other stars that are even younger. Even if we know that they have very short lives, that doesn't mean that they've gone away already. For example, the Pleiades. The Pleiades up here, 400 odd light years away. That's Alicone in particular. These are all very bright blue stars. And they're quite young, they're quite new. They've just burst out of their envelope of gas, their star-forming region, their stellar nursery. So they're all, a few hundred light years away, 382, 383. They are physically pretty close together. That one's closer to 400, but they're all within, 3 to 4,500 light years away. And they're only going to last for billions of years. They're going to last a very, very short amount of time. But millions of years is still a really long time compared to the 400 years away in terms of light speed that they are. So even though those stars are some of the most short-lived, they're still burning when you see their light. And that's true for the vast majority of the stars that we see in the sky. What's not true is that they twinkle, or that they actually twinkle. When you look at the stars in the sky, they appear to twinkle, absolutely. But once we remove the atmosphere, that twinkling goes away. It is the atmosphere that distorts the light of stars. So if somebody asks you, do stars twinkle? Well, from our perspective, yes. When you look at a star in the sky, the atmosphere distorts it. That's what causes twinkling. You could also say, do stars twinkle? No, they're big balls of burning gas or plasma going through nuclear fusion that are sending out light pretty evenly. Except, of course, for when they're not. Is this Algol? No, that's Hamal. Algol, there we go, is the Eye of the Demon, one of the brighter stars in Perseus, and it is an eclipsing binary star, which means that it's got two stars orbiting around each other, and they can appear brighter or fainter depending on their arrangement, depending on whether or not they're aligned with each other. So that's a star that still twinkles, or I suppose winks or blinks. It is supposed to be the Eye of the Gorgon, the Eye of the Demon, so winks or blinks might be more appropriate, but its brightness does change over time. It's one of those tricky questions. Do stars twinkle? From our perspective, yes, they do. Do stars actually twinkle out in space? No. But a lot of these questions can be a little deceptive. There is a right answer when you're speaking with the right terminology, but if you're not specifying exactly what you're talking about or how accurate or how pedantic you want your answer to be, things can get a little bit fuzzier. So the sun, for example, isn't yellow, it's white, unless you're looking at it from the Earth through our atmosphere. The stars don't twinkle unless you're looking at them from the Earth through our atmosphere. And the sun isn't a burning ball of gas. It's a burning ball of plasma, as long as you include the heat generated by nuclear fusion as a form of burning, because most people, when they say burning, they don't necessarily mean oxidation. Physicists absolutely do. And of course, 9 times out of 10, 99 times out of 100, down here on Earth, if you see a fire, that's oxidation. But you're just going to say fire, you're just going to say it's burning. And of course, that is meaningfully different from nuclear fusion, but not when we're that far away from it. It's a really hot ball out there in space. It provides us heat. That's really the important thing. So I guess one more. Out in space, nobody can hear you scream. Unless you're on the International Space Station, which has its own packet of gas. Again, all of these questions can be a little bit deceptive at times. I'm going to take a quick look at the moon. Just so that I have something that looks nice. Here we go. There's the moon. Two astronauts standing next to each other on the moon, shouting at each other. Without any atmosphere, they probably wouldn't hear each other. But if there was an explosion near them, they'd still feel the vibration. There's solid matter here that vibrations can't travel through. So if you shouted loudly enough, or if you smacked a hammer off the ground, other people could feel that vibration, as long as the spacesuit was thin enough. So in space, yeah, no one can hear you scream if you're actually floating in the vacuum of space without being surrounded by a packet of gas, like most people in space are. And even then, if there's a big enough bang, you might not exactly hear it, but you can still feel the vibrations as long as there is some matter for them to be transported through. And pressure waves may propagate even through the near vacuum of space, because space is really only a near vacuum. That is less of a misconception. A near vacuum, a place where the concentration of atoms is so low that particles just pop up into existence. The physics can get very, very weird, and that, of course, complicates the answer. But even with the answers being weird or complicated or dependent on your perspective, I still hope that you enjoyed this video. And if you'd like to read some of the details behind these weird questions, you can check out my website, grievingscontent.ie. And if you'd like to see more from my channel, or even if you don't, I hope that you like this video and subscribe to my YouTube channel, because I hope that I'll get to see you back here next time.